Good afternoon. This is your 6th digital class for the subject physics. Now, last class we discussed about electric field and electric field intensity. Now, let me continue our discussion by considering the topic electric field line. Now, electric field we have defined as a particular region surrounding a charge within which the influence of that source charge exists. So the intensity of electric field, because the field intensity varies from the source charge. So if you have to define the field intensity, what you have to do, as we discussed in last class, you have to place a unit positive charge. So if you place a unit positive charge, what will happen? If the source charge is your positive in nature, then definitely a repulsive force gets experienced on the unit positive charge. So that force is nothing but the field intensity. So let me try to define electric field line. So definitely electric field lines represents the influence of electric field. So as per the definition, it says that electric field line is a straight or curved imaginary line. These are the imaginary line to represent the influence of the source charge or the influence of the field. Electric field line is a straight or curved imaginary line in a region such that the tangent at any point on the field line gives the direction of electric field at that point in the region. So if we consider this figure, we have placed a source charge plus Q, and these are the arrow. Now how will you explain this arrow? This arrow can be explained by considering the definition of electric field intensity. Now if we have to define the field intensity at this point, because this charge is your source charge, definitely a field will generate surrounding this source charge. So if you have to define the field intensity at this point, what will happen? What you will do? You will place a unit positive charge here. So if you place a unit positive charge here, what will happen? A repulsive force will get experienced by the unit charge. So the direction is out of the source charge. So the field intensity at this point is outward direction, or the force at this point is outward direction. So this arrow definitely means define the direction of the force experienced by unit positive charge, or you can say that this arrow define the direction of the field intensity. Similarly, if we consider a source charge as your negative, what will happen? If we place a unit positive charge here, so what will happen? That unit positive charge gets attracted by this negative source charge. So the direction is towards the source charge, which is negative in nature. So this arrow basically define the direction of the field intensity. Okay. So the field is there and this arrow is define the field intensity. So electric field lines are nothing but an imaginary line to predict the direction of the field intensity. So if you place this system, one plus Q, another minus Q, so what will happen? Here the field is outward and here the field is inward. So in between positive and negative charge, the field from this field line is from positive to negative. But if you consider this one as a system, what happened basically? This part, this arrow part is towards this entry of this means this arrow part is towards the negative charge and this arrow are away from the positive charge. So if you consider this is your entry and this one is your exit. So this system, if you consider, then it directs from negative to positive. So this system is nothing but a dipole, and sometimes it is asked what is the direction of the dipole. So basically dipole directs from negative to positive charge, because these arrow are the entry you can consider and this arrow you can consider exit. So if you consider this system, one entry, another one is exit. So direction is from negative to positive. Now let me try to define few properties of electric field line. So I think most of you know two electric field line never intersect each other. What is the reason? Because at that intersecting point you do have two direction of the field, which is absurd. That's why two field lines never intersect each other. And second property is this one. For positive charge the field line is outward, and for negative charge the field line is inward or towards the negative charge. Now you can classify, it says the electric field lines begin from positive charge and end on negative charge. And classification, you can get uniform and non-uniform electric field. Uniform electric field can be represented by parallel field line, and non-uniform electric field can be represented by non-parallel field line. So it has the same magnitude and direction in all over the region or at every point within the region, of the field, and non-uniform electric field has different magnitude and direction at different point, okay, within the field. If you consider the field and if you have to define the magnitude and direction, in uniform electric field it remains same throughout the region, but in non-uniform electric field the magnitude and direction changes. Now if the field line is crowded at a particular point, it means the strength is high. Now this is all about your electric field lines. Now let me go for electric dipole. So it says that a pair of two equal and opposite charges separated by a small distance is called an electric dipole. So this is your dipole. Now all of you know that in neutral atom, positive charge and negative charge coincide. But if you apply electric field on the neutral atom, what will happen? Separation of charges occur, and that creates the dipole. One is your positive one, another one is your negative. So in case of atom, the center of gravity of positive charge is your what? Nucleus. Proton resides, and center of gravity of negative charge is also there. That is nothing but the electron within the atom. So if the center of gravity are separated by certain distance, then that creates a dipole. But if they coincide, then it becomes a neutral. So electric dipole has a dipole moment. So it can be defined as the product of the magnitude of either of the electric charge and the dipole length. That is your P vector equal to Q2L vector. This is a vector quantity, as we have shown here. It directs from negative to positive. Now dipole length is a vector quantity and it directs from negative charge to positive charge. Okay, so this is another topic. Now let me continue this topic, electric field intensity due to a dipole. So electric field intensity due to a dipole you can define by considering this figure. You see, AB is your dipole. One is your A. At place A you do have a negative charge, and at B you do have positive charge. They are separated by certain distance, that is your 2L. Now O is the midpoint of the dipole, so LL, the distance is your, one is your here to here L and here to here L. So we have to define the field at P, and P is nothing but the axial point, because if you consider this one is your axis, so P is on the axis, so this is your axial point. So if you have to define the field intensity at P, what we will do? We will place a unit positive charge here. So if you place a unit positive charge here, so what will happen? That unit positive charge get repelled by this positive charge. So the field direction is out of P, that is E plus vector, it directs outward. So if you consider negative charge, this is your unit positive charge, so the unit positive charge get attracted by this negative charge, so E minus vector, that is your towards A, you can consider. This is your E plus is towards BP and E minus is your towards PB, you can consider. So if you have to define the field intensity at P due to individually positive and negative charge, you have to use that expression which we have discussed in last class, that is your E equal to KQ by R square. Now if you consider P is your point, so E plus is your KQ, and what is the distance from positive to P point? That is your, if it is R and if it is L, then R minus L whole square. This is along BP. And if it is E minus vector, then it is your KQ R plus L whole square along PB. If you consider minus Q, then it becomes easier, here to here R and here to here L. So R plus L whole square along PB. So if you have to make this one BP, then you have to insert one negative sign, that is your KQ R plus L whole square along BP. So total field, because now E plus vector and E minus vector is in same direction, if you consider these two terms, so you can get the total field by adding these two. So E plus vector, E minus vector along BP. So if you substitute this one, KQ 1 by R minus L whole square minus 1 by R plus L whole square. So if you take the LCM, it becomes easier R square minus L square whole square, and if you simplify, it becomes 4RL. So if you split this one, 2KQ and 2LR, just I have simplified this one because Q2L is your dipole moment, as we have defined here. Q2L is your dipole moment, so I have to express this expression in terms of dipole moment. So that's why 2KQ 2LR, R square minus L square whole square. Now if you consider R is very greater than L, then you can neglect L square. So it's soon R square means R to the power 4. So 2kp R by R to the power 4. If you can simplify R4, then it becomes your R cube. 2kp by R cube, and this directs along BP. Okay, so now let me go for this topic, field due to the equatorial field due to dipole due to the equatorial point, means at the equatorial point you have to define the field due to the dipole. So this is your diagram, this is your dipole, and equatorial line is a line which is perpendicular bisector. So this is your equatorial line, and P is at any point on the dipole. P is any point on the equatorial line, and this is your dipole. So if you have to define the field intensity at P, what you have to do? You have to place unit positive charge here. So this is your negative, so it gets attracted, E minus vector. And if you consider this one positive charge, so it outward. So this is E plus vector, and this is your E minus vector. So if you consider this one too is your adjacent sides of a parallelogram, then this one gives you the resultant field which you have specified E vector. Now here we have considered theta. So exterior angle is your 2 theta. So if you find the E plus vector, then it comes out to be your KQ R square plus L square along where? Along BP. That is your, because unit positive charge and positive charge, so repel, so outward. And if you consider negative charge and this one, so it is attracting. So EKQ R square plus L square, because this is your R and this is your L. So if you consider the hypotenuse, it's your root over R square plus L square. Now as it is a square, that's why root over goes off. It is your R square plus L square. Now if you have to define the resultant field, then what you have to do? You have to use that condition, that is your vector addition, a square plus b square plus 2ab cos theta. So here a square plus b square, so this square plus this square, so it comes out to be your 2 times, because same magnitude, and 2ab, ab is your same magnitude, so this is your square, and angle is your 2 theta, so cos 2 theta. So if you take out the common term, so kq r square plus l square comes out, and root over 2 1 plus cos 2 theta. So 1 plus cos 2 theta is your 2 cos square theta. So 2 to 4 cos square theta. So it comes out here 2 cos theta. Now you can define cos theta. If you consider cos theta, base by hypotenuse. So base is your what? L, and hypotenuse is your root over r square plus L square. So if you substitute this one here, so what it comes? It comes out to be your KQ. This is your L. This is your 2. So 2L, this is your root over R square plus L square. So in denominator is R square plus L square. So R square plus square 3 by 2. This is your 3 by 2. So it's your PK by R square plus L square 3 by 2. So as R is very greater than L, so it comes out to be your PK R square goes up. This is your R cube. So finally you are getting PK by R cube. That is your field on the equatorial point of a dipole. Now let me go for this numerical. It says that in a hydrogen atom, the proton and electron are separated by distance. This one, find the dipole moment of the atom. So you have to use this expression, that is P equal to Q2L. Dipole moment is denoted by P, so Q2L. So if you substitute P Q2L, so it comes out to be your P. Q is your magnitude of electron and proton charge. Either one you can consider, 1.6 10 to the minus 19 coulomb, and the separation is your 5.29 into 10 to the power 11 minus 11. So if you simplify this one, it comes out to be 8.464 into 10 to the power minus 30. That is your coulomb meter. Q for coulomb, and this is for meter. So this is all about your, this is the number 6th digital class for the subject physics, and these topics are very important. Please go through this topic and find out any queries, any doubts. So you can ask me in the WhatsApp group. So more we'll discuss in next class. So go through this topic thoroughly and very carefully, because these are very important for your coming exam. Thank you.